Hopefully you can all hear me. So I started out at University of North Texas. I'll just give you a quick background of where I come from. So I got a Bachelor of Fine Arts in Ceramics and a Bachelor of Fine Arts in Sculpture. And I made a living as an artist for a couple of years prior to studying Metallurgical and Materials Engineering at Colorado School of Mines, where I got a bachelor's. Then I went to Northwestern for Material Science and Engineering and got my PhD there. And then I did a 1-year postdoc with the Art Institute of Chicago, and I did 2.5 years postdoc at Ruhr Universität in Bochum as a part of the Alexander von Humboldt Stiftung Foundation. And my PhD was joint with Argonne National Labs, so I did a lot of synchrotron work. After that, I came back to the U.S. and I was at ATI Huacheng, which is now Specialty Alloys and Components. And there I worked as a metallurgist, and then I was also teaching at Oregon State. And then after that, I came back to UNT, and now I've been at UNT for about 8 years in the Material Science and Engineering department. So a lot of the work that I'm going to show today comes from these various places, and then also within my own group, and then with collaborations like NASA and ARL and AFRL. Okay, so I'll go to the next slide. Let's just give you an overview of what I'm going to talk about. So I'll get a little bit into what are shape memory alloys, the applications, the characteristic properties, multifunctionality aspects of it, current issues, some of the alloying and processing effects, structural control, how do we do that, then some of my technical expertise and capabilities within our lab, and then the current projects and my research group. We'll go here. So just a brief overview of what shape memory alloys are, what they can do. There's sort of 3 properties that we think about. The first one's a shape memory effect. So that would be looking at this right here. We're basically taking a twinned material, twinned martensite, we load it, and then we get deformed twinning or deformed martensite, which allows us to get sort of this large strain without damage. Then we can unload that, and then we heat and cool. And so heating and cooling moves it into the austenitic stage, then comes back to the original shape. So that's our ability to remember its shape, or the shape memory effect. So that's one aspect. Pseudoelasticity, that's over here. And so in the case of the martensite, we're starting in this condition. In this case of the austenite, we're starting in this condition, so B2 cubic. We load that sample up, then it goes through this austenite to martensite phase transformation, which is goes along here, and again, this allows us a large amount of strain. Most metals can only do about 1% strain. We can go out to about 6%, fully recoverable. Then you unload it, and it goes back through the transformation, and then returns to the initial state of austenitic material. So that's pseudoelasticity. Then solid state actuation. That would be us loading the material and then heating and cooling. And so then you can do sort of this load biasing, and this is where actuation devices come in, which I'll talk a little bit about that. And you can see it in the mechanical loading, the behavior of SMAs. You can also see it thermally, so this is heating and cooling. So we start in the martensite. As we heat it up, it transforms to austenite, and then as we cool it back down, it goes back to martensite. So we can start in this condition or this condition, but these are the transformation temperatures, sort of the things we look at. And this work, a lot of the work that I'll be talking about comes from 2 of my former PhD students who have thesis. He just graduated. He's working at Raytheon now, and he works at ATI, Matt Carl. Okay, so I'll go to the next slide. So here, just again, the solid state actuation, just to show you sort of where this lies in comparison to other materials. This is the shape memory alloy. This is actuation stress, and then actuation strain. And so you can see you get orders of magnitude more stress and strain in the material, so higher potential of use here for these, particularly for actuation devices. And you can see like where other like shape memory polymers are a little lower. And again, if you look at those units, this is an order of magnitude, so we're going up, 2 orders of magnitude here in terms of power that we can put into the system, or work output, let's say. So I'm going to go to the next slide. So, and then this leads to a lot of different applications, aerospace and structural. This is work at Boeing, and NASA also does work like this. So we're got wires, cables, actuators, couplers, dampers, and then medical devices is prosthetics, stents, clamps, staples, those kinds of things. Engineering us thermostats, cryogenic applications like with refrigeration. And then also in the oil and gas industry, there's lots of different places where these may be used. So that just gives you sort of an idea of the different things you can do with them. Okay, and then another aspect of it is that it is multifunctional, or you can take advantage of multifunctional aspects of this. And so what that means is we may use like the shape memory effect in combination with like a biocompatibility, corrosion oxidation resistance, hardness strength, impact resistance, energy absorption or storage, damping or sensing. So you may use the effect and also use it to sense things. And so there's when you use these, you can think about more capabilities than just whatever you're trying to do.
Gotta let the thing reset. We don't have any internet right now. It's resetting right now.
Oh, sorry. Okay.
The internet is not on right now.
What does that mean?
That was a bit of feedback. Go ahead. I think that was unrelated to the presentation. Carry on.
Oh, okay. Sorry. All right. So, so some current issues. These are various issues that we are working on with shape memory alloys and things that we're currently addressing. And I'd say a lot of these we have a very good, the community at large, so with shape memory alloys has a good understanding of how to address these, but they are ongoing issues. And so like fatigue life, this is one where we want to extend that. So we're looking at ways to do that through like, looking at non-metallic inclusions and precipitation effects. And then processing. Then there's also training stability. So as I show over here, as you cycle the material, you can see that it's sort of drifting. So this is the first cycle, second cycle, and so on. And so this does stabilize, but we're looking at why and how do we control that. And then we also are looking at strain rate effects. So the behavior changes as you increase the rate of loading on it. And so we've done some studies on those. And then one of the big features is fine-tuning those transformation temperatures. And so one is to push them to higher temperatures. Another one is to make the hysteresis, so the width between these two peaks, either narrow or wider, depending on what the application is. And so within our group and within the shape memory community at large, we have different ways of doing that. And one of the other challenges is processing of these ternary SMAs. So we want to fine-tune the properties a little more. We also have to worry about how can we do this on a large scale, on a production scale. So again, so now we've looked at applications, the characteristic properties, multifunctionality, some of the current issues. Now I'll talk a little bit about the alloying processing effects, so some of the things we do there. And so again, with any SMA system, small amounts of other elements can have profound effects on the properties. And so I just sort of listed out two of the more common ones, nickel tie based, copper aluminum based. I'll focus today just on the nickel tie based. And you can see there's a lot of different elements we add and they do different things. So this one increases R phase, this one widens that hysteresis I mentioned. And that's good for like coupling devices. Down here, these are the high temperature alloys, so you put these in and you can increase the transformation temperatures. The reason for that is you don't want accidental actuation when it gets hot. So if we can push those temperatures up a little bit, we can avoid accidental actuation and have a little more control of it. I'll go to the next slide. So if we're looking at these nickel tie based high temperature SMAs, one of the things we can look at is alloying effects. And so in this case, we have gold, palladium, platinum, hafnium, zirconium. These are the main elements that do that. They substitute for, so the first three substitute for nickel, the second two substitute for titanium, and then they have their own processing issues. And so the processability has been greatly improved though. And so these were, for a long time, these were considered not processable, but I'll show today that we figured out how to do that. And you can see here, this is just showing as we add hafnium to a nickel tie alloy, that temperature goes up. So we can move the transformation temperature up pretty high, and we have a good control of it. The other thing to look at is the cost itself. So it's much cheaper to use hafnium. It's much cheaper to use zirconium. And then the density as well, they go down with both of these. And so that's also another factor to look at when you're looking at these alloys. Okay, so now I'll talk just briefly on one of the studies we did with ATI. And this was a nickel tie with 20 atomic percent zirconium substituting for titanium. And we're looking at different temperatures. So this is processing effects. So basically, we're looking here, if you hold it from 0 time to 15 minutes, what changes? And so we're looking at the oxidation effects and the phase formation. And I have also here, we coupled that with SEM images, so you can see them over here. And mainly what we are trying to address is that you get cracking in these alloys when you try to roll them. And so what we found is if you go too low, you can have H-phase precipitates, and this will make it so that you wouldn't be able to roll the material, or it would make it difficult, could lead to early cracking. And so we need to go to hotter temperatures. And so when you do that, 700, 800 seem to be okay. When you get to 900 and 1000, you start getting this phase segregation. And this has to do with this sort of complex oxides that form. And so you can see there's multiple layers of oxides that form. And that leads to a segregation. And ultimately, you get this intermetallic formation. And this intermetallic formation will result in cracking. I think I have it on the next slide. Let's see. Well, and then I zoomed in here just to sort of show if you look at what's happening at the different temperatures, there is this sort of secondary oxide that starts to form. And that doesn't really happen until about 900. And so we think once this oxide starts to form, you start getting this separation of the zirconium that pulls out. And then you start forming these intermetallics down here. And these intermetallics end up leading to cracking. So I can show some of that here at 1000. We tried to roll this piece, and you see it sort of snaps off. At 900, you get these little fine cracks along there. And if I were to keep processing that, I would ultimately get fracturing along that sample as well. But if we do it at 800, we have no problem. So we can just run it all the way down to small wire, fine wire. And that was for zirconium. And that was a NASA project. And then also another NASA project we looked at was, we did this with zirconium. Now we're doing it with hafnium. So 20 atomic percent hafnium. And again, we took a sample and rolled it down. We applied the knowledge that we had here. We looked at the SEM images in our samples and those, and also saw the similar phase separation and these oxidation forms that happened. And so basically the same kind of thing happens. And so we're able to also draw this down to really fine wire. And we ended up doing hot rolling and then some cold drawing to get fine wire. And the purpose of this was to make springs that we would use as actuation devices for applications for NASA. And so we can also make those wires. We can take those wires, we can turn them into powders. So the advantage there is you can get pre-alloyed powders. So the composition, this material is very sensitive to composition. So if you're off a little bit in terms of the nickel content or tie content, you can get very different properties. And so one of the advantages here is that I can make the alloy that I want, and then I can make the powders that I want from that alloy. And that's using a hydride-dehydrate method, where we hydride the material, it becomes brittle, and then we crack it. We also found that we could make little micro actuators using this technique. And the way we do that is once you have the hydride in, the material becomes brittle. And so if we then initiate the phase transformation happens in it's like Luther's-like bands. And so it propagates stepwise along the surface, and it does it sort of in a helical fashion. And so if you make the material brittle and you transform it, you'll get this cracking, and it has to do with the way this shears. And so you get sort of a consistent angle, and you can then make small micro actuators out of these. The next slide. So then here I'm looking at structural control, and so this leads to like grain refinement. And so one of the methods that we use is ultra fine grained wires, and I'm not going to talk about that study today, but I'll talk a little bit about like strained glass alloys. And so these are similar in that we're doing pretty severe cold working to the material. And what we find is that there's sort of an ultimate range that you want to aim for. And so what happens is thermally, if I continue to load this, so it's kind of hard to see here, but this is the red curve is the edge received material. As I put in about 15% cold work, it decreases that peak. I go to 30%, it decreases even more. At 45%, we see the phase transformation completely disappear. And so when we cycle the temperature, there is no phase transformation. That's thermally, you see no phase transformation. But mechanically, we still see that it loads and behaves like a shape memory alloy, so fully recoverable. And so we went to look at SEM here, or TEM, it's TEM here, and you can see you've got these sort of larger twinning structures that as we continue to load the material, we break those up. And eventually we get down to where we have nanometer size twinning in the material, little regions where they can twin. And so what that ultimately leads to is normally when you load the sample here, you would see sort of like hot spots. And so all the loading would happen at one spot in like the as received material. And again, I mentioned it does sort of like a Luder's-like band loading. And so this has a video, but the video is not working. But what I would tell you is what happens is you see these sort of propagate across the surface like this, as in a helical pattern across the surface. And it usually starts at both ends, and they kind of run and meet together. In a normal as received material, you'll get a hot spot where like you have a defect or something, or a non-metallic inclusion, and you'd get early fracture there. And so it would initiate there, and so your weak point would be here, and like these regions may never be even loaded. And so with this strain glass alloy, we can basically make it such that it propagates through the entire sample completely, and it remains evenly loaded. And so you don't really see any variation until it fells. And so that's sort of the advantage of going to these strain glass alloys. And that can be very useful in damping because it increases the energy in which the material can absorb. And that's something we're doing with the Army Research Lab, where we're trying to look at how much energy this can absorb. All right, let me go to the next slide. And so here I'm just talking about precipitation strengthening. So one method is this nickel 4 Ti3 precipitates. So you take a nickel-rich alloy and then you precipitate out these this secondary phase. And so without that, this is what your phase transformation or your pseudoelastic material looks like. You don't get full recovery. With the precipitates, now I create a little mini strain field around, and that allows me to get much better recovery. Or full recovery of the material. And this is similar. There's other things we can do, like the cold working would do a similar thing. That's the grain refinement. There are multiple ways in which we can achieve this, but it's something we have to think about when we're designing the material.
Hello?
And I also look at porous structures and composite structures. I don't have time for that today, but I just mentioned that we do look at those things. So similar to the nickel 4 Ti3, we look at H-phase precipitates. And this is sort of highlighting, we do a lot of work with the synchrotron, so the advanced photon source. For my PhD, I was funded by the APS, and so I was at the synchrotron. I was basically a beamline scientist and ran a lot of experiments there, and so I continue to do a lot of that work. And there we can do combined techniques with diffraction, imaging, fluorescence, small angle, wide angles. I've been doing a lot of that lately, where we look at the amorphous phases and the crystalline phases at the same time. So interactions between those phases and what they do. And then also we do in situ experiments where we do heating and cooling, where we can do electrochemical processes. We can do hydriding. So there's a lot of different things we can do sort of in situ and observe changes in behavior, changes in the material, and really understand what's happening. So in this case, we take the diffraction pattern, we convert it to this D-spacing, then we isolate and focus on these sort of smaller peaks. So this is a nano precipitate that forms H-phase peak. And we can map that and see as it changes over time. So over 3 hours, we see it increase in size, and then we can use field refinement to figure out how the precipitate has grown, and we use Xray equation to calculate that. And so this is just showing you sort of how we can non-destructively map a precipitate growth. Here's growth and coarsening. And so the material coarsens over time, and it starts at about 10 nanometers, goes to 25 nanometers. And then we coupled that with TM experiments and see that, like, from the TM experiments, we see that there's sort of, so the equation that we use here assumes that particles are spherical, which is not actually true. So we're also working on refining this equations to match better what we see experimentally. But you can see here, like, the estimated thickness is about 30 nanometers. Our measured thickness was about 25 nanometers. So we're on the same scale. The disk diameter we don't capture, which is 90 nanometers. You can see the particles there. Okay, so for the next slide. So now we're going to talk a little bit about some of the technical expertise and capabilities I have in the lab. And I've kind of talked about that already a little bit, but I'll mention it again. So we do a lot of development, characterization, processing of alloy, porous, and composite structures. Those are some of the things we're looking at. And then we also tie this to neutron laboratory and synchrotron X-ray scattering techniques. So these are non-destructive testing where we can observe some of the things that we see in the other materials. And like I showed earlier, we use it to figure out things like how to process material, what's changing in the material when we do a heat treatment, or what changes when it's exposed to oxygen or hydrogen. So different environments, so we can sort of understand what are we changing and how's it going to affect the structure. And then in terms of characterization, we'll do mechanical testing or thermomechanical testing to better understand what's actually happening. Okay. Yeah. So we also look at we can make these sort of porous structures. So this would be for damping applications where we're going to be absorbing load. So if you had a high impact. We also do a lot of processing where we can make different structures, and we have a lot of control over that. This is the high strain rate deformation that I mentioned. So if you were experiencing like a ballistic application where it's high loading, we look at how does a material absorb that and what changes, what can we do to improve the response of the material, how do we change it. Have atom probes so we can do a little more in-depth, how does the, so in this showed earlier, we looked at how do the precipitates form and what's changing at that interface. So then in terms of like some of the like military applications, for example, for dampening or loading, we make these foams where they have a continuous structural interface between the solid foam material. So you don't have a distinct interface. It's sort of a continuous network. And that will enhance thermal conductivity. It enhances more efficient heat transfer, improve mechanical properties. So if we were going to use these for actuation devices, for example, if you wanted to move a wing flapper or something like that, or you want to open a solar panel, one of the challenges is if you make these sort of thicker parts, they're going to have a heat distribution where you might not get even transformation. If we make them more porous, we have a larger surface area and we can get a better response in terms of the phase transformation efficiency. Another aspect of it is we can embed these shape memory alloys into a material. So I can have a structural material where I put these particles in, and as I show over here, we can basically, this is just changing the temperature, but I can also change this stress plateau based on the combination of alloying elements I use and heat treatment. And so what that means is that I can set it at a specific stress, let's say 500 MPa. This material can be damaged and I may not see it. It may look perfect, but if I go do non-destructive X-ray analysis of the material, I may see that I've got a phase transformation in here. So I've got austenite here, and then I have martensite here. And so that tells me that the stress in this region is at or above 500 MPa. And so while it may look okay, I know that it's not. And so then I could take it out of service and fix it before it actually gets damaged or destroyed. The additional effect here is that we are also able to use that as a precipitation strengthening mechanism where we can add additional strength to the material. And there's lots of ways to get these powders or particles or wires into the material. Those are things that we also look at. So if that was of interest, I could talk to you about how we might do that, where you might want to do it. Maybe there's a specific region that you're concerned about damage, then we could look at ways to embed particles into it so that we could use this as a method to know when we've reached a certain strain and when we need to replace the part or repair it. Then we also do a lot of neutron laboratory synchrotron X-ray scattering, and so I just am showing a bunch of examples here of different things that we looked at. So like we can do, if you want to understand, a ternary quaternary system, what does the phase space look like? What sort of structures can you get? We can do that relatively quickly with the synchrotron. We can make a sort of compositionally graded surfaces and then map those out and tell you, this is the state of the material here, and here it changes. So it sort of defines like phase boundaries, those kinds of things. So those are things we can do. And then of course you can then tie this to nano indentation and other laboratory techniques to sort of look at things. We can also track with synchrotron. We can track phase formation and its morphology. So how does it form? How does it change over time? And so like in this case, I'm showing an H-phase precipitate that has sort of this star-like cluster. That happens and then it goes away, and then a more stable H-phase comes back in. So we look at that sort of thing. We can also do like in situ fracture mechanics, looking at phase distribution, and then also how does the stress in the individual phases look and orientations. And I mentioned the different techniques. So we can put our sample in, we can do fluorescence, we can do this X-ray diffraction, we can do both wide angle, small angle, and we can also do imaging, so you can couple all that together. So for example, if I want to look at damage evolution in a composite or in a structure that has phases where there's a density difference, we can look at how does the material become damaged and how do those two phases interact. So the load partitioning between the phases. And so that's something that may be useful. In terms of phase transformation, we can also track that and see how it's happening. So here I'm mapping the interface between the strained wire. Basically, I load the wire and then we mapped over the interface. And so we can identify how the different crystallographic orientations interact with each other and how they transform with each other. Okay. So I think I'm almost done here. Let's see. So there were a lot of different people that were involved. This was student work, and I tried to put their papers on the slides. So if you're interested, you can always go back at the slides and see the different students that worked on these projects. I did a lot with ATI, shape memory alloy components, Argonne National Labs, NASA. I'm also involved in a University Leadership Initiative program with NASA, where we're looking at these high temperature shape memory alloys for actuation devices for like wing flaps and for noise reduction on an airplane, those kinds of applications. Let's see what else. I do a lot with Ruhr Universität in Bochum. They've done a lot of shape memory alloy work, and I continue to work with them. I usually go there every summer. I should be going there next week, but of course, because of the coronavirus, that got canceled. So I'm not sure when I'm going, but I plan to go back again. I also do work with ARL, AFRL, and then let's see. And I'll just mention some of our current projects. So we're doing processing characterization of high entropy alloys. We do these field responsive properties of adaptive strain glass alloys. This is with ARL. We do processing of high temperature shape memory alloys. This is the NASA ULI. Precipitation is shape memory alloy wires, and this is for spring applications for NASA. We're looking at lead-based battery materials. We also do a lot of different types of foams, so shape memory foams, along with other types of foams within these materials. This is also with ARL. Then we have some surface modified bioresorbable zinc-based porous structures that we make for stent applications and biomedical applications. And again here, they're also used for battery and applications as well, for zinc ion batteries. We also have looked at some current projects with welded stills, so two stills being joined. We're looking at that for NETL. We did have a project on superconductivity that's sort of ending, and we did some high entropy alloy laser cladding process, and that one's sort of ending, although we applied for new funding for that. And then I have some random projects that we also look at with music and art. Yeah, and this is my group. I think with that I'll stop. I've kind of ran long there. Anybody have any questions for me?
Yeah, so thanks for that, Dr. Young. There are some questions that have trickled in the chat. I'm not sure if you're able to see them, but I'll kind of help moderate and list them all for you.
So the DoD applications, so we are looking at damping applications on that, and that was leading to the strained glass alloys. We also looked at high strain rate deformation, so how does that mechanism work? So those are some things that we're looking at. Let me see what of the materials process. Yeah, I mean, the strained glass alloys, we still want to look at how that's happening, and we are in the process of doing that study now. But there's a lot of work there that still needs to be done, and understanding how the material responds to these sort of high strain rate loading. Okay, do other countries explore shape memory alloy research? Yeah, so I do a lot of work with Germany. Previously, so let's see. So as a part of my research at Argonne National Labs, I had the opportunity to work on shape memory alloys there. And then I ended up doing a 2.5-year postdoc in Germany. And so I'm fluent in German. I taught courses there, and I also did a lot of research, and we were mainly focused on shape memory alloys there. And they have, the way they do research, they fund for about 3 years at a time, and they had about, I'd say about 60 people working on shape memory alloys. So it was very helpful to be working with them and continue to work with them, because they are moving at a fast rate. And so, like I said, I continue to go there usually every summer, and I was planning on going, and obviously things got changed. I still plan to go maybe in September if it opens, and if not, I'll wait till next year. But that is I do a lot of work with them and keep in contact with them about that. And they do a lot of shape memory alloy research. I think the Italians also do some, and I've worked with some of the Italian groups that are doing shape memory alloys. We have a consortium for the advancement of shape memory alloy research and technology. And so there's a website for that, and we have almost weekly meetings for different groups. So I lead the processing group. We have a multifunctionality group. We have just the general one. We have a design working group, and the consortium is casmart.org. Or ksmart.org, however you want to say it. And there we discuss these things, and we talk about different things we can do with the alloys, and sort of what are the challenges. And so I know some of the people on here are actually in that. And that is, yeah, pretty helpful in understanding sort of where we're at with things, and what are the challenges that we face. So let me see, what's another question?
The next one was about if you've evaluated.
Yeah, okay, so I'm looking at sort of effective SMA particles, loading on polymer, ceramics, and metal composites. I have not done, so I've done this on porous structures. I've not done it on anything embedded. I am interested in that. I would like to do it. I've done it a lot on like non-SMA materials in terms of, like, my thesis was on aluminum composites, and on other composites, iron and iron carbide. So certainly taking the foams that we make and putting them in a polymer, or adding a ceramic, or making a ceramic preform and doing sort of metal infiltration into that. Those are things I'd be interested in, but no, I've not done that yet. Okay, so embedded SMA particles. So on that question, there's sort of a question here about what material system has been embedded with SMA particles. That's aluminum, so it's easier because the aluminum's sort of low temperature. I think the low temperature alloys are easier to avoid having the material melt away. But that's something we could do. I think when I've looked at those, I think they work well, but they're a little tricky to do. I don't know that you'd necessarily want to do it on a large part, just because it would be costly, but maybe you would. It depends. But I think if you know sort of where you're most concerned about stress, you might want to embed them there, and then you would have a way to non-destructively evaluate the part. As I mentioned, when you get to a certain, we can basically tune the stress to a certain level. Uh-oh, what's happening? Music going. Is that playing me off? Okay, so
sorry about that. Must be somebody else. I got it.
So you can basically tune the stress plateau, so we know that at this stress it transforms, and then we could use that to figure out sort of where we're at, and if we need to service the part at that point. I hope that answered your question. Let's see. Main limitations on using additive manufacturing for high temperature SMA manufacturing. Yeah, so that's a trick. The issue is with evaporation, and so you may lose nickel, so you may have to add more to it. So you may end up needing to tune your alloy to be sort of off composition and then try to do it. The other thing is it's very sensitive to like nickel content, for example. Within 1%, I can change the temperatures almost by 100 degrees C. So that's where I mentioned earlier, you may want to start with pre-alloyed powders so that you have a fixed composition rather than just relying on nickel powder and tie powder sort of shooting in and mixing. And so that was the reason for us developing a technique for making shape memory alloy powders. Let me see. I think that's one of the big challenges with them. Many research, or is there a potential for using SMAs to couple materials with dissimilar CTE? So they do make coupling devices for shape memory alloys. They're nickel tie niobium. This is done at my former company ATI. Within those, you sort of get a one-time strain, and then you get the shape memory effect. So what that means is that we wrap it around, it sort of creates a strain around the material, and then it has the ability to move through the phase transformation so that it maintains sort of some mobility but keeps it, or flexibility, but keeps it sealed. And so what they do with that is they'll have it in a cryogenic temperature, and then you bring it out, put it on the part, it'll clamp down, and then you're ready to use it. And the way that works is the niobium sort of forms a soft phase in between the shape memory alloy, and so that sort of gives you some elastic range to work with before you take advantage of the shape memory effect. So that's for coupling materials. Consortium is, and I can post it on here. It's Casimir.org. Okay, somebody else already did. So Casimir.org.
Yep. Yeah, perfect.
Possible to share slides from this webinar. Yeah, I think they can be.
So looks like the last remaining question here from the chat, at least, is can you touch on the possibility or limitations in scaling?
Yeah. So that's something we sort of developed, and I mean, I'm really interested in it. We haven't done a whole lot of work with it. I would like to do more. It was sort of I was funded to do the powders project, and I discovered this while I was doing the powders project, and I'm definitely interested in exploring it more, but we haven't been, well, I guess I should just say I haven't been funded for it, so I haven't done a lot with it. We've done a little bit. I'd like to do more because I think it has a lot of potential, but I need the right application for it. So if you're interested, you can talk to me more about that. And we are looking at, I showed just one, but we were looking at it to apply it to, copper-based alloys, iron-based alloys. So it's a mechanism effect and not a material-dependent effect. So as long as it has shape memory, we're able to do that. And that opens the door to other materials and other applications. Let's see. What other questions are there?
Okay.
Is there
Yeah,
another one that I had answered?
that might be it on the list of questions. And quite frankly, we're getting here to the end of our time limit, and I wanted to respect the reservation and time that we had for everybody. So if there are any other questions, as I mentioned to everyone, DSIAC, we do a technical inquiry research service. So if there's any questions on this particular topic, questions you want me to pass along to Dr. Young, would encourage you to go on our website, DSIAC.org. You can submit your question that way. You can email myself, Brian Benish, our contact alias. One way or another, get us your questions, and we will help support you. And otherwise, we can, if you have questions for Dr. Young, you can reach out to him individually for that as well. So unless you have any other kind of parting words, Dr. Young, I just thank you for your time and the opportunity to give this presentation.
Learn something, and we certainly can collaborate and help with any sort of applications you have with the shape memory alloys.
Very good. All right. Thank you, everybody. Thank you.
Thank you.